Ok, André, pode começar, avisa, já tá. Hello, everyone. Welcome to one more seminar of our graduate advanced seminar series in computer science, Advances of Computing at Unicamp. My name is Cláudia Bowser Medeiros, and I'm a professor here. And there's also Professor Edmundo Madeira, who's right here, who coordinates the series of seminars this semester. And today, we have the honor of having a distinguished speaker, Roberto Di Cosmo, who is in Paris looking at us and visiting us all the way from France. And Roberto is a computer science pioneer, and he's going to show us very spectacular results of his unique initiative, Software Heritage, whose premises is that software is part of the world heritage. This, as you will see, his talk involves advanced research both in, among other things, software engineering, databases, data architectures, computer architectures, and other things. So, Roberto, thank you. And he has so many facts and important things in his CV that I asked him to present himself. Okay. So,
Okay.
yeah, he's not presenting himself because he says, I'm not able to. I am not able to because he has done too many important things. So, Roberto, thank you very much for visiting Brazil virtually, and we hope you can come and visit us soon in person. So you can start, and can people interrupt for questions, or do you prefer to have them at the end?
Well, maybe it's easier if we have them at the end because
Okay.
the remote is complicated. But
Okay.
do not hesitate to take down any question you want.
Sure. And the other thing is, do you want me to tell you the time, like before, 10 minutes before, or you
Yeah,
have?
sure. Sure, that would be great if you can
So
just.
we organize about 40-minute talk and 200 hours of questions. Is that it?
Fantastic. It will be a pleasure.
Yeah. Okay. So you can start right now, and thank you so very much.
Thank you. Well, first of all, it's my pleasure to be virtually with you, and thanks a lot, Professor Claudia, for the invitation and the other for the organization. So today, let me start by giving you sorry, here, giving you a short presentation of myself. I'm a computer scientist and a theoretical computer science at the beginning. I spent some kind of 30-something years, more than 30, unfortunately, years doing research and teaching in different areas. More than 20 years in open source and free software, and more than 10 years trying to build infrastructure for the common good, either organization or software. So there are a few items I had decided to put here. I mean, the first live distribution of GNU Linux is something I developed some quarter of a century ago, for example, but now the most important activity I carry over today is related to software heritage, the initiative we are going to talk about today, but I'm also a member of the National Committee for Open Science here in France and was leading the Task Force for Infrastructure for Software at the European level. Well, so let me start a little bit about software, which is a key item in our presentation today. You know very well the software is all around us. Of course, it's actually the fabric that brings together our digital lives. But what people usually tend to forget is that software doesn't come out of the blue. It is actually the result of human.
Roberto, I'm sorry
Yes,
to interrupt. We are having some communication gaps, so maybe you should speak a little bit slower because some syllables are missing when you
okay,
when you
no
speak.
problem.
Okay.
Let me
Thank you.
try
I'm
again.
sorry. I'm sorry.
No problem. Okay, well, I will try to speak slower and louder. Let's see if it works. So we're saying when you think about software, we need to remember that software is the result of human creativity, and actually it is created by humans in the form of source code. So as Harold Abelson, who is a professor who wrote a book that I was using when I was a student, is the sound okay now or not? Okay,
It's perfect.
fantastic. Okay, let's go. So in his book, in the introduction to this book, you saw this phrase. He was saying the software in the programs must be written for people to read in the first place and only incidentally for machines to execute. You can think of this as a professor telling the students that if they turn in homeworks that cannot be read, I mean, they will get a bad grade, but actually this is deeper than that. If you look at some important pieces of historical source code, for example, this small extract of the 60,000 lines of code that were on the lunar module in the 69 to land the man on the moon, I mean, you see on the left, there is assembly code that goes to the machine. On the right, what you see is actually comments in plain English after the number sign that have no meaning for the machine, but are intended to carry a message to the other human beings that will need to read, understand, evolve this software later on. And of course, you can think these messages from human to humans are only needed when you are actually writing assembly code. If you have a higher level language, maybe you don't need it. Well, this is not really true. If you fast forward some 30 years later, so this here is a piece of mythical source code which was part of the Quake 3 arena first-person shooting game developed by John Carmack at ID Software. This is written in C, which is a much higher level language than assembly code. So you have variable names, you have functions, but you see still here the name of the function, the name of the variables, and the comments are very important to understand what is going on. You know, here let's say, okay, some comments are clear, other are not exactly so clear, but they are pointing you to the part which is difficult. I mean, we could spend the afternoon looking at this piece of source code, which was used to compute 1/square root of x efficiently on machines without a numerical coprocessor. But I just want to show you that even when you have high-level programming languages, comments are important. And in particular, you see this line, this last line here, has been commented out by the developer because it is no longer needed. So you will never find it in the binary, you will never find it on the machine, but it is important to understand. And in particular, if you look at this, you start understanding that there is some Newton method applied here somehow, okay? But I mean, to sum it up briefly, as Len Shustek, who was a board director of the Computer History Museum, wrote in a beautiful piece in 2006, uh, the access to the source code of a piece of software provides us with a view into the mind of the designer. That's precious. The real knowledge is actually in the source code, even if, of course, we want to run the software to use it. So the big question is, how important is software in research today? Well, you know, that has been a strange story. For a long time, people have used software in research, but didn't really recognize it as an important part of what we do in research. Well, today we have really objective data. This has been developed by the French Ministry of Research over the past 2 years. They did an analysis of all the research papers in the past 2, 3 years with French authors to understand where software is actually used. Okay, you have machine learning models that run on the PDF files and detect mentions of software. And even if I mean, here the fonts are too small, For example, the area where software is most used is in bioscience, for example. You have computer science, you have earth sciences, physics, chemistry, social sciences, geography, psychology, everywhere. Software is everywhere in research today, and it is one of the three key pillars for open science. You have the articles, the research articles, the papers. You need open access to them. You have the data, which is fundamental. So you need access to data, open data, well structured. But we also need access to the software that is used to analyze the data or to produce the data or to convert the data. And of course, the links are important between the papers, the article, the data, etc. So of course, software is a special object in research because it can be a tool, a piece of software that I write can be a tool for another team. It is a research outcome of my team and can be the object of study of still another team that does software engineering, for example, want to understand how it works, what are the principles. And of course, to do this, we need access to the source code. And for reproducibility, we also need access to the history of how software has been developed. You do not read 1 million lines of code from start to end. You usually enter into that by looking at how software has evolved, who added what, when, why. Well, now that we know that software is important, in particular in academia, but in the world globally, the big question is, how are we managing our software? Well, not so well. Okay, if you look in academia, we have issues with reproducibility, with maintenance of software, etc. Here in these slides that I will share, every word or text in blue is actually a link. You can click on the link and get to the supporting evidence. But I collected here a few articles that actually do research on the software that is produced and used in academia, and they pinpoint a lot of issues. Lack of viability of source code, lack of reproducibility, problems in maintainability, etc. But also, if you look at industry or public administration, we are not doing well either. And there are issues about security, integrity, vulnerability, traceability in software. Here I put a little bit of collection of major issues that made the headlines news, but there are many. And so there is a big issue about tracking the software that we build, we use, we sell, we integrate, and to understand where vulnerability comes from. So luckily, after a long time, awareness about the importance of this is raising at the level of public policy. So for example, in academia, there is an emerging policy framework for software inside open science. So in 2019, for example, at UNESCO, there was a Paris call on software source code. We had 40 experts coming from all over the planet in different areas, working for a long time to produce a declaration that you can access by clicking on the blue link. And among the other many subjects, there is the issue of recognition of software developed by researchers. Quality software developed by researchers should count in the career of academics. And later on, you also find software mentioned as a key point in open science in the declaration, in the recommendation for open science that UNESCO published in November 2021. At the European level, you see the European Open Science Cloud, which is a specific initiative I do not have time to comment on. And here we had a special report on infrastructure for research software. They highlighted the importance to actually have a common archive, and we will come to this. This is software heritage. But more recently, you see software popping up all over the place. So there was a special track on software on the Open Science European Conference. There is a software present in funding mechanisms for different countries in Europe. NASA unveiled an open science policy with software in December 22, and so on. I mean, always going on. Now, you may ask, okay, software is important. What can we do to handle it better? Of course, there are many aspects. Let me focus on some simple ones. There are some simple but fundamental needs for software in open science. The need number one is to make sure that the source code of the software we develop is not lost, which is properly archived and can be found when needed. This is important for reproducibility. If I read a paper that says, I took this data, I applied this transformation, and the answer is 42, if I want to check it later or improve on it, I need to find the software that was used to get 42 as an answer. And if I get 55, where the problem comes from? I need the software to understand if it is a bug in the software, an error in the data, etc. But software evolves over time, so it is not enough to archive the software. I also need to understand which version is really important, which is the version that I used. So I need a precise identifier to find the precise version. Again, this is important for reproducibility, so archival and reference. But then you also need to have a proper description of software to make it easy to find it and to reuse it. So this is important. There is metadata description about this. And last but not least, you need to find a way to credit the people that contribute to software. So find a way of citing software the same way we actually cite data or cite publication, which is not the same as referencing a software. So when I'm interested in reproducing a result, I really do not care too much who wrote it. I just want to get the good version of the code, compile it, run it, and use it. But when I write a paper and I want to credit the people providing me with the tool I'm using, I need to cite the software, and this is different from referencing it. Well, how did we do archival and reference in the past, and actually even today? When I was much younger, even actually before I became interested in computer science, in the 70s, 80s, we made software available on the internet using something which was called FTP, the File Transfer Protocol. Probably nobody of the young students here ever heard about it. I mean, because it's been phased out a lot of many years ago. There are still few FTP servers around. Then we had the web. So people put the software on their web page. But the problem with web page is that you change the URL, the web pages go away, so it is not very, very stable. And later on, since web pages were not stable, people started using document archives to put zip files with something like a digital object identifier on it to try to limit the problem. But this is not really adapted to software. So in the 2000s, we started using software forges, platform used for doing collaborative development. You know it, like GitHub, which is very popular today, but many other were there available before. So some people put software in institutional projects, forges, other on commercial or free forges out there, Bitbucket, GitHub, GitLab, you name it, which are much better for developing software. And so more recently, you have, for example, the ACM, the Association for Computer Machinery, implemented a mechanism in the digital library to allow you, when you have a paper, to actually deposit the source code in there, which is kind of a strange way of doing things. If you look here, this is an example where I have redacted the information of the authors. So you see, you have a paper, you have an artifact, a software artifact associated, you get two nice badges, the artifact is available and functional, but then the only information you get is a DOI that nobody uses in software development, and the author is forced to smuggle in the link to the GitHub repository in the description. And if you want to get the source code, you need to actually go and download the zip file, which is not what you want. Actually, you want to go to a forge to get the right thing. And so all this is not very satisfactory because A, gives a very poor experience, B, is fantastic for development, but it is not an archive, we'll come to this, and C, is a strange thing which is not yet the right thing to do. So why am I saying it is not enough to put your software on GitHub to do your job? Having archiving reference. Well, because forges are not archives, okay? And we discovered this in 2015 very, Very brutally, when Google Code, they have 700,000 projects hosted, and Gitorios, they have 120,000 projects hosted, actually shut down with very small, very little wording. So this brought a lot of broken links in the web of knowledge, including in my papers that were pointed there. And this was not just a one-time event. So in 2019, Bitbucket, another forge, announced the phasing out of Mercurial, and this led to removing over 250,000 of projects, all of a sudden. So you put your project there, you go on holidays, come back a little later on, and it has gone. And that's terrific, and it keeps coming. It also happened to a forge in our own institution at INRIA. So if you want an archive, you need an archive. You cannot use a forge thinking it is an archive, because it is not. And luckily now we have one. And so if you look just at these two parts, archiving and referencing, now finally we have an infrastructure that addresses this issue. And just to let you know, I mean, I split the talk in two parts. There is a part which is on how to use software heritage for handling issues related to open science. And another part is why software heritage is interesting actually for doing research on software. Let me focus on the first part. So what is software heritage and how can we use it for open science and reproducibility? Well, software heritage is an initiative which was started in 2015, so almost 10 years ago, with a clear mission to go out, collect, preserve, and share all the source code which is publicly available. In a nutshell, this means building a reference catalog where you can find all the software which is out there. Doesn't matter if it comes from GitHub or GitLab or an instance of GitLab or Bitbucket or Debian or Ubuntu or Red Hat or a package manager, PyPy, NPM, whatever. Single place where you find all these things, a single catalog. Second, an archive. Software which is in software heritage stays in software heritage, doesn't disappear. It's not like a project on GitHub that you can remove or a forge that goes away. And last but not least, we'll come to this. This is the first piece of such an important research infrastructure we need to build and make available to do massive scale research on software evolution at scale. I mean, our friends in astrophysics managed to build incredible infrastructure to observe the sky. We, in computer science, we need an infrastructure to observe the galaxy of software development. So this is an international initiative. It has been built in collaboration with UNESCO. There are many organizations that support it. And actually needs, of course, funding, and the way it is funded, it is supported by INRIA, which is my home institution here in France today, together with some 20-something international organizations. You see there are all over the planet, not yet in Brazil. We'll hope to find also partners in Brazil that contribute to this effort. And it is designed to be one single archive shared. Okay, single infrastructure which is open, common, and addresses the needs of a lot of different applications, from cultural heritage, rebuilding the history of computing, to industry, to research and public administration. It is today the largest archive of software ever built. Actually, the picture is not up to date. We have over 290 million project archive. All software is stored in a single graph. We'll come to this. There are over 19 billion unique source files archived. And this comes from many hundreds of different platforms around the world. Of course, the biggest one, you find them here, GitHub, GitLab, Bitbucket, and so on. And it is a very complex infrastructure. So what we do, we actually build adapters to connect to many different code hosting platform or code distribution platform out there. So one for GitHub, one for GitLab, one for Bitbucket, one for Debian, one for Red Hat, one for PyPy, one for etc. You name it. To list the projects that are available there. But then these projects are maintained using different version control systems. For example, Git, Mercurial, Subversion, yes. So we do an extract step to extract from all these different version control systems all the information in the structure for doing the rebuilding the history, and we put all this in a uniform single data structure, which is a gigantic direct acyclic graph, technically a Merkle graph, which means each node is actually identified by a cryptographic signature, which is built from its components. And this today contains all the history of development of software across the world in a graph that has more than 35 billion nodes and 500 billion edges. It is probably the biggest social graph available today. Social because software is built by humans. And each of these nodes, the files, the directory, etc., is identified by a specific identifier, which we call the software hash identifier. If you are a user of Git, these are basically glorified Git hashes, but the only point is that we made it more understandable. So you have a prefix, a version, a schema version, an object type that says what this hash is identifying, and this can be a content, a directory, a revision, a release, a snapshot. And we also added context information that allows you to say this particular file in this particular directory, in this particular project, as found in this particular moment, and even go into the file and saying, I'm interested in line 7 to 29. Okay, and because I remember we deduplicate all the files, so the same file can appear in thousands of projects, and this context allows you to say where you want to see it. This is actually a standard that has been adopted in industry in SPDX. There is a Wikidata property for that. It is undergoing ISO normalization as we speak today. And you can click on some examples. So let you, for example, you remember this Apollo 11 fragment of code we have seen together before? I can click here and I get immediately, directly into the archive. This is actually the software heritage archive, and you find exactly the lines of code that we have used in our presentation before. And you can get these links all over the place when you are visiting the archive. Now, if you let me go forward here. And so imagine what you can do with a paper. You are writing a paper, it is a part of your argument, it is very important. You want to link to that part of the argument, make sure it will stay, will not go away as if you point to a forge today. Well, you can just get the identifier, put in the paper, and this is really a game changer. You can find the information on how to do this in this how-to, which is very detailed. And now, this is really, really different from a traditional archive. You can browse the software source code that we had seen before. Let me do it full scale here. So, for example, you see when you are in the archive, you know where the software has been found. When was the last version of the archive taken? You can see how many times it has been visited, all the different kind of visits. Of this particular repository over time. When you go to the code, you can find the history of development of the code, all the different versions, all the different branches which are available. You have the impression you are working on a forge like GitHub, but this is actually an archive. Okay, you can completely use it. And the other interesting point is that, of course, you can reference the software at all levels of granularities. And the interesting part is that, of course, we do automated harvesting. Okay, so we don't go out and collect everything that we can find as much as efficiently as we can. But sometimes people can ask to have their software archived using functionality that are called the save command functionality, or using the update software edge browser extension. I do not have time demo for you all this, but you can click on these links to see what happens. You can also set up webhooks to automatically archive your code. There are journals and open access portals that actually interact with the archive to archive the software associated to articles in particular way. But the importance of having automatic harvesting is really high, because sometimes, let me show you this example here. You see this guy, let me see. If I can get, you see, this is actually a tweet by an astrophysicist researcher when Bitbucket removed all the repository used with Mercurial. He said, okay, somebody told me that the code associated with the paper of mine was down. I thought everything was lost, but luckily somebody already archived it, and so it is still available today. You see, so this is important to have automatic archival. Now, if we can look at some adoption indicator, and I will speed up a little bit because I want to show you also the other part. There are some analysis has been done on collection of papers by people, for example, in the life sciences. They found in a selection of papers 6,000 software mentions. Most of them go nowhere, so they link to URL which disappeared already. Then they found 1,000 links to GitHub and already almost 400 links to software heritage directly on papers which are published even before we were doing advertising. Today, people that do reproducible science, for example, in computer graphics, you have this initiative which is replicabilitystamp.org. Whenever a paper has been checked and the software validated and actually does what it is intended to do, they have a DOI to the paper, a pointer to the repository, and a pointer to the version archived in the archive. And there are regulations here in France that push a researcher to actually ensure software is archived in there. Well, okay, so just to close the first part on open science, the good news is that now finally we have the right way of doing archival and referencing in a very, very easy way. You can archive and reference every piece of software you use, even small scripts, not necessarily big projects. And so here we have all the pointer to the how-to. But you can also describe inside software by using specific metadata. So there is a code metagenerator here that would require more time to go over here. Here in France, we also connected this to the open access portal so people can actually get reports for their curriculum, or for application, or for grants or funds, or what software they built just automatically through the connection between the open access portal and software heritage. And there is a LaTeX package for citing software available today. So what is left, as always, because academia doesn't move very quickly, is to train students, to train colleagues to actually use all this. But now I would like to spend the last 10 minutes, because if I'm correct, Claudia, I have 10 minutes left, despite that. Okay. So I would like to spend a little bit of time to show you something of the incredible thing you can do when you use software, not just for archiving software that you want to point to for research, but actually when you want to do research on software. And let me start by telling you something. You know all this big graph I was mentioning to you before, these 35 billion objects, 500 billion edges? Well, this is actually available as a graph dataset. The software heritage graph dataset is available on the open dataset infrastructure provided graciously for free by Amazon. So if you go on AWS, you can find a bucket that doesn't require any account or to access. And there you find regular dumps of this graph dataset that we produce every few months. I mean, we try to do it at least a couple of times a year for use in research. I mean, of course, this you need to accept the ethical charter, the terms of use, etc., etc. But after you do that, you can actually work on this directly on Amazon Athena. So let me give you a very simple example. So imagine that you are doing research in software engineering and you are asking yourself, what are the most popular commit verbs used by developers? But what I mean, when you do a software development, you commit a version and you have a log message. In this log message, the good practice is to use the first word as a verb that says what you did and what the patch does. So for example, the commit says, fix the bug number something, add the functionality number something, etc., etc. So you might ask, what are the most popular commit verbs? Without software heritage, what you would need to do is to actually go and download hundreds of thousands of repositories from GitHub and other places, download them, put it on a cluster, extract all the log files, then extract all the information, doing work. I mean, you are in for a year of work. Well, by using the graph dataset available on Amazon Athena, let me do it live for you. Here, what you do, I'm connecting here to the Amazon Athena console. And here you are. You see in this interface, you can access the graph information as an SQL database, which is stored in an SQL database. You have a table for the content that contains the hashes of the file, the information, etc. For example, here we are interested in the table for the revision. These are the commits. Inside the revision, you have a lot of information, like, for example, the author, the date, the committer, the date, etc. But you also have the message. This is a commit message. So you can write a nice query in SQL like this one. I do not know if you can read it very easily, but you can select here from no, this is not the right. This is not the right thing. Let me hear. So this is the right way. So I'm selecting from the revision table the message, so the log message, but the log message is binary, so you need to convert it from binary to string, trim it, remove and take only the first word, put it to lowercase, take the stem of the word to make it better as a presentation, only take commit logs that are less than 1 million characters. You may say, who writes 1 million characters in the commit log? You won't believe it, what people do. Okay, so we take a small one. This is a word. And then actually, we take only non-empty words. We group by word. We order by the number of currency, and we take the first 20. So what is your guess about what is the most popular commit verb? Look at what is happening here. Behind Amazon Athena, there is a distributed SQL query engine, which is called Presto. So it is being running on a cluster. The price model, you pay $5 per terabyte scanned. So we are starting to pay almost 50 cents here. You see, 100 gigabytes. We are getting to 50 cents. Let's see how much it cost me to make this demo. But that's it. It's done. So 124 gigabytes. So it's maybe 55 cents. It took 33 seconds to run. And here are the results. So 400 million commit logs start with update, 214 million start with merge, 193 million start with add. You see, update, merge, add, fix, bump, create, initialize, remove, change, delete, new, commit first, etc., etc. See, well, okay, this is not the most interesting thing that you can do, of course, but I wanted just to show you how trivial and easy is to do this kind of massive scale research when you have such an infrastructure. This was impossible before. Now it is possible thanks to the work we are doing by creating this graph. But then I imagine if you follow the course of Claudia or Edmundo, you know that putting a graph in an SQL database is not necessarily the best thing you can do. Because in SQL, you cannot really ask, for example, all the descendant of a node, because this is a transitive closure, which is not expressible in first order logic. But So we did something else. Actually, this was done by Stefano Zacchiroli, Sebastiano Vigna, Paolo Boldi, Antoine Pietri. They actually adapted bleeding edge technology, which is used to do graph compression of the graph of the web, to the graph of software heritage. Today, the result is that this incredibly big graph can be stored in memory, in RAM, in central memory, in less than 300 gigabytes. So the transversal time is super fast. And you can do very interesting things on the graph. The only have the structure of the graph. If you want more information on the metadata, you still need to go off to RAM. But this is again something which was could not even be imaginable 5 years ago. You can access this using Java or gRPC. Rust interface is coming, and all the documentation is available under this link. So since now I have just a few minutes left, so this was a sneak peek to some of the inner working. I mean, this graph database, the compressed graph that we use to actually trace origin of the software, but there is a lot more. You know, for example, now there is an issue about cybersecurity. I mean, when you have millions of projects and every single piece of application that you write use dependencies that depend on other dependencies, and you have so many different components coming into a project that you do, a minor bug in one of the dependency can endanger all the system. Okay, and so we need a way of tracing vulnerability across all the software commons. And this is what is done in a project that just started today, a few months ago, which is called Software Heritage for Security, Tracing Vulnerabilities. So there are many things to do in there, but there is also another application and using all the source code which is stored in Software Heritage as training set. I mean, actually not everything, you need to select the part that you can use to build generative AI models. And actually this is what happened a month ago. So a big collaborative project, which is called Big Code, built on top of the Software Heritage Archive, a subset which is called the Stack V2, which was used to be StarCoder 2, which is the best OpenAI model for coding that you can find today. There are three versions, 3 billion, 7 billion, 15 billion parameters. The 3 billion parameter is something you can run on your own desktop machine with no particular difficulty. And of course, if we want to go into that direction, there are a lot of challenges in expanding the infrastructure, because now we are talking about big data, how you do query efficiently across all the graph, across all the metadata. How can you integrate all this information that you have in the Software Heritage Archive with other knowledge bases, like, for example, information in the research articles, information on Wikidata, Wikipedia, on Stack Overflow, etc., etc. So this is a huge, huge challenge that lies in front of us. So if I can get to a conclusion here, what you have seen here, it was very short, of course. I mean, 10 years in 40 minutes is not easy to do. I hope to give you just the desire to learn more. This is, for us, is really a part of a grand vision. What we would like to do is to bring together industry, governments, academia, communities to build an infrastructure for having better software for the future and better research in general. And software energy is really the first element for doing this, because everything is open, it is vendor neutral, it is worldwide, it is designed to be long-term, it is non-profit, and it is already enabling archiving, referencing, integrity verification, and we can build a lot of things on top of it. But of course, this is just the beginning. We need a lot more for this. And actually, you can help doing this. You can use archive, you can disseminate information about what is archive, you can actually build and adapt research tools on top of it, you can tackle some of the research challenges which are behind it. And to do this, you can join this growing and active community. The picture you see here is the core team working on software heritage here in Paris. But there are many ambassadors all over the planet that talk about the project that you can contact to know more. There are contributors. This is an open source project, so people are actually free in contributing. And actually, we even have open position for people that want to come and work with us. There are engineering positions which are open um, in here. You can find the links in the slide that we share. And if you want to learn more, there is an annual report which is available online, a short video that tells a story of software heritage, and even a nice animation built by a Brazilian colleague that shows the evolution of the source code of our infrastructure, not of the source code that we archive. So I think with this, I have used up my time, and I think I stick to 40 minutes precisely, if I'm not wrong, Claudia.
Yes, you did. Congratulations on a very, as usual, very interesting presentation. And in a very short time, you covered 10 years. Okay,
Yeah.
so in next 10 years, then you'll still have to cover them in 40 minutes again. So this is, you'll have to compress your mind code. Tem perguntas? Tem pergunta na web? Ou... Não. You said one thing that I have a couple of questions. The first one that intrigued me is that you say you do not have copies. Okay? So suppose now that I decide to deposit something in GitHub because you have interfaces that will extract code from GitHub, right? And then you will get my code. How will you know that my code has not been deposited in GitHub or in any of those sources before? How do you check for copies so as that you have unique copies?
Yeah, that's a very important. Thanks for the question. So, the way our harvester work is that we go around, we see the new project that we find. When we get this new project, we check the hash of each of the components of each of the directory, etc., and we compare with what we have already in the archive. So if it is already present in the archive, we do not store it again. Now, of course, if we connect to advanced forges that use something like Git, there is a protocol that allows us to know what is new and what is not new without even downloading anything. But if I get, for example, a zip file or a tar file or a package somewhere, our loaders do this job. So we get a copy once, we check what is new, what is not new, and we only store what is new. And for something which is not new, we do not store it, but we remember that we have seen it again. So we keep a link in the archive that says, okay, this file also appears in this other project there.
Oh, okay. So you can keep, and now if you do have that, you can find out where some code has been used, right?
Absolutely. This is one of the other magical applications of this huge graph. I mean, since all this graph is deduplicated, at some moment, a particular file content is stored only once, but we have all the links that point in there from the places where it is used. So you can navigate into the archive, navigate into the graph, and find the different places where it appears. But to navigate such a big graph, you cannot just do it by using SQL queries, okay? It will take forever to such a big graph. And here is where this compressed graph in memory comes in. So if we had more time, I could even show you a demo how this works. It's kind of fascinating to have this tool that allows you in a few seconds to see where the software appears in all the in all the archive.
Yeah, we can always invite you for other talks like every week. No, not every week, of course. One practical question is, you said you can deposit. How can institutions set up some sort of agreement with you, or so that their software repositories would be merged or harvested by you.
Yeah, sure. This is a very interesting point. Let me show you a little bit. I mean, to show this, I need to do this and then that, then this. Okay, very interesting question. So we go out
Nothing,
and
nothing is.
harvest.
Oh, okay, okay. I'm sorry.
Now,
Yeah, let's
now,
wait. Now we can see it. Yeah.
so of course we go out and harvest everything automatically for the thing that we know. But imagine there is a piece of software that we do not know and that somebody would to ask us to archive. So there is this functionality in the archive which is called Save Code Now. You can go here and say, hey, there is a repository maintained under Git or CVS or Bazaar or Mercurial or Subversion, let's say Git, that is found, for example, here. I want to archive it now. So you click on Submit. You see, and it goes into this list of requests which are pending and will be archived in the couple of minutes, in the next couple of minutes. You see, since we opened up this functionality, there have been already over 1,300,000 requests that has been made. Now this is, it's annoying. You need to go manually point to the URL, etc. So another way of doing things is, for example, if you go,
Just to interrupt right now,
well,
that means that anybody in the world can ask for you to archive their software without any agreement.
yes, to archive, yes.
Okay, no, no, that's amazing.
And then you see, for example, here is an example. This is a project of mine on GitHub. Let me put it bigger. Do you see this little green thing, this little green icon here?
Yeah, yeah, yeah.
This is a browser extension, which is available for Chrome, for Firefox, for Edge. And if somebody wants to port it also on Safari, would be very welcome. That actually checks on the forge where you are there, what is the last commit, checks on the archive if it is archived or not, what is the last archival, and then the color tells you how things are going. For example, here green means that the archived version is current. It is the same as the version which is here. Yellow would mean it is archived but not current. You just click it on it to get it. Gray would mean it is not archived. So for a piece of software which is important for you that you find and you want to make sure it is archived, you just click on this icon, it will be archived automatically. If it is a piece of software yours, you can set up webhooks, but as you said, there are more general applications. For example, you would like to archive the forge of the University of Campinas, and you cannot do it one line by one line like this. And for doing this, we have this extra functionality, which is called Add the Forge Now. It is a form that allows you to request us to archive automatically your institutional forge, for example.
Ah, okay.
But to do this, you need to create an account. It is a little
Yeah,
bit more
yeah, and
complex.
have some sort of agreement, I imagine, right?
Yeah, absolutely. So I wonder if this answered your question.
Yeah, 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 yeah. It's just, and how do you ensure that, for instance, suppose my expertise is to write malicious code to destroy things, and then I ask you to archive it. Um, you will probably archive it, and you will be harming the whole world, right? So how can you have? Of course, you know me. I exaggerate, but how is there any way of avoiding that?
And this again is still a very important, interesting question. So we asked ourselves what to do when we started this almost 10 years ago. And so this is, Software Asia is kind of a special archive, a typical traditional archive, if you look at national archives or libraries, etc. They actually do a selection of the material which is archived before archiving. Because it's, you have limited space available. You need to make sure that, being in the archive is kind of a stamp of quality. While on our side, since there are so many dependencies between code and code can start very little and then become bigger later on, we take the opposite approach, which is we archive everything we can get. And being in an archive is not a guarantee of quality. So, for example, there is bogus software, there is malicious code, of course. The quality will come later. So later, you need to have a portal, you need to have search engines, you need to have tools that allows you to say, I want to find a piece of software with this and that particular quality. Even having malicious code is important because then you can track vulnerability easily. You want to know where the malicious code is and where it
Okay.
is located.
Okay. So, my last question, because nobody's asking questions here. No, no. Oh, okay. Davi, você quer? Ai, você. Agora já estou aqui. Gosto de sofrer. Ah, okay. So I'm going to translate his question. He is a very bright undergraduate student we have here. Suppose that by mistake, he asks you to um, archive a piece of software that should not be archived. Is there any way where he can say, "Oh, I'm sorry, I made a mistake. Please delete it"?
Yeah, sure. Of course, when you build an infrastructure like this one that has a worldwide scope, you need to take into account this kind of situation. There are many situations when we end up archiving software that should not be archived for many reasons. I can give you two or three examples. One typical example is you have a private company that has a subcontractor. This subcontractor, by mistake, puts on GitHub a proprietary piece of code that belongs to this company. Then the mistake is discovered, maybe 2 months later. Okay, so we have already archived the software. They remove it from GitHub and they found out there is a copy on software architecture. So we have a mechanism which is called the takedown request. So it goes through a process which says a special address in connection with legal team, etc., that evaluates this kind of request and implement the removal request when they are legitimate.
Okay. Yeah, he said it's exactly what he was thinking of, this kind of situation. Can you give, well, you said that you were looking for people to work for you, um, contributors, and so on and so forth. So if you can share the material with me, we'll put it online. Okay. Tá bom, obrigada. So my final question, because there's no questions from from YouTube, is can you give us some data on volume in petabytes, in exabytes, and whatever? And you also mentioned when I visited you that there was a mirror in Italy,
Yeah,
right?
absolutely. So, well, there are some interesting studies we did a few years ago to look at how the amount of data in the archive grows over time. The interesting thing of this particular graph we are maintaining is that since every file is stored only once, every commit is stored only once with its earlier date of appearance. It's kind of easy to actually go over time and see when a file appeared for the first time. And we do not need to do any deduplication because the system is already deduplicated. And so by doing this analysis over a period of a few decades, we saw that in the last 20 years, the size of the archive was growing by something like 100% every 22 months. So it doubles in size every 22 months. Today, the file contents, I mean, the biggest part of this graph are the file contents, then the internal nodes is much smaller, is almost 2 petabytes, compressed in a simple way. So each file is compressed with gzip normally. So 2 petabytes is big, is small for my friends in particle physics, because when they do an experiment at CERN, every experiment is 4 petabytes of data. But for us, 2 petabytes is significant. And the particularity is that the files are small. So you have almost 20 billion tiny little files that end up occupying 2 petabytes. And the usual object storage that the people find around are not exactly designed for this kind of payload, because they usually are used for images or videos. But, the medium size of a source code file that we have in the archive is 3 kilobytes. So it's pretty small.
Okay, I did not expect that. 3 kbytes is nothing, right? I mean, if you consider size, 3 kilobytes for size is nothing, and yet you have medium size. So yet you have billions of files of 3 kbytes. So
if you look around, I mean, some source code files are pretty big. If you look at the Linux kernel, I think the biggest file last time I checked was over 1 megabyte. That's a huge, huge piece of source code written in C. But many other modules or source code are pretty smaller, much smaller. You try to have things organized in separate files. And so we need an object storage which is adapted to this particular kind of things, in particular if you want to do massive analysis of the source code. You need to access the data fast.
Okay, so since there are no more questions, tem lá na frente. Oh, I'm sorry, I'm speaking Portuguese. But you speak Italian, you speak Spanish, you speak French, so you understand Portuguese.
No, if you speak slowly, I can try, but I do not guarantee. Okay.
Roberto, first, thank you very much for a great talk. I want a question about a project. I think it's an ongoing project. Stack V2, you said, yes? You commented that this project is producing the StarCode 2 in generative AI interface. I'm curious about this tool. Is this tool available? What's the idea behind the tool? What's the expected result? Is the challenges to build this tool?
So let me give you an example. So I'm sure you are all familiar with ChatGPT, GitHub Copilot, all these kind of things. Of course, everybody is using it in everything. Well, these objects are closed, so nobody knows exactly how they are built, on what data they are built, how it works, etc. But there is one particular project, so let me share with you so you can see it. There is one particular project which is called Big Code that you should see. Let's see. You should see it now. Okay.
Yeah, we see it now.
So you see, you go on huggingface.co. This is basically the GitHub for machine learning. Hugging Face is a platform that everybody uses for data set, for modeling machine learning. One of the many projects there run by Hugging Face and ServiceNow is called Big Code. And this is the initiative to actually build open machine learning large language model for code. And so, for example, StarCoder 2 is this one. So you have the paper with all the technical details. You have the 3 version of the models that I was mentioning. And this is built using the Stack V2. The Stack V2 is the 67 terabyte of source code that has been extracted from software heritage. And that you can find it here, for example, you see. And this is the result of a collaboration we had between us and the people in this big code project. All of this is available. You can use it, you can try. And actually, if you want to test this, let me see if I can find it. StarChat, where is StarChat 2? Let's see. So this is a version of the model which has been trained to do something like Copilot, okay, or ChatGPT. For example, you can say, write a, what do you use? JavaScript program function to compute Fibonacci numbers. And you see, and here the chatbot is answering you. Here is a simple JavaScript function to compute Fibonacci number using recursion. You see, JavaScript function, etc., etc. This function works by recursively calling itself with Smiley number. Okay, this is not the way you should write Fibonacci, you know. I mean, because otherwise it explodes exponentially immediately. But I mean, it is a program. It actually, this is just a test, a demo, okay, because it is costly to run this project. But you can download the model and run it yourself. You can read the paper and see exactly how this has been built. And the collaboration we had with the people in Hugging Face Service now is to work together to help them select the appropriate content from the Software Heritage Archive to do this kind of training. But all the machine learning has been done by them, not by us. I'm not an expert.
Yeah.
You see the kind of thing you can do, that's fascinating, the kind of thing you can do here.
What also fascinated me, and that's the end of it, okay? Because you know I never stop. It says it was based on code written in 600 languages. So I could ask for, instead of Java, some obscure language nobody has ever heard of, right?
The point is that if you look at the content of software Azure, since we archive a lot of software comes from different places, not just GitHub. Okay, GitHub is the biggest one, but there is also software coming from many, from hundreds of our origins. You can find all code written in all the languages that people don't use anymore. And so when the people in the Big Code project actually did an analysis of the selection of software they took, they identified more than 600 programming languages. But if you, I don't know if you are familiar with this small working group in the ACM, which is called HOPL, History of Programming Languages. If you go on hopl.info, you will see that they count more than 8,000 programming languages that exists. I'm not sure we had an example of each of them, but there are
600 is already quite a lot. So, Roberto, I'd like to thank you so very much for your time and for showing us so many interesting things. And even though I spent 2 days with you, I learned lots of new things today. So there's lots of things to do. There's lots of things to learn. And I hope we can start some sort of collaboration between Unicamp and you guys. So thank you so much.
Thank you, Claudia, and everybody. And I would be delighted to see collaboration starting up. You know, I mean, what we do is really as open as possible. We are very transparent what we do. We look for collaboration. Of course, sometimes you make mistake. Okay, this happens to everybody, but actually we are very transparent with this, and we would be delighted to see collaboration in different formats forming in the future. So
okay, so in Portuguese, tchau. Okay, that's Portuguese. Italians invented it after us. Okay, so that's Brazilian Portuguese. Tchau, tchau, or bye bye.
Tchau, alla prossima.
Até a próxima. Muito obrigada. Bye bye.
Bye.
Obrigada a todos.